Welcome friends, Igor is here, and in this video we will consider the operations of matrix addition and matrix scalar multiplication. In this lesson we will define the vector space of matrices of a fixed size. We will define two operations on matrices, matrix addition and matrix scalar multiplication, and we will discover that these two operations satisfy the same 10 properties as similar operations for column vectors. Let's get started. Let's recall that a matrix of size m by n is a rectangular array of numbers with m rows and n columns. The first number in the size of the matrix is the number of rows, and the second number in the size of the matrix is the number of columns. The vector space M sub Mn is the set of all possible matrices of the fixed size m by n with entries from the set of complex numbers. We will say that two matrices of the same size are equal if they have identical entries in all positions. Note, for two matrices to be equal, they have to have the same size. Here is an example of two matrices, both of which have the same size 2 by 3. They are equal as matrices because at every position they have identical entries. These two matrices are not equal to each other, even though the matrix C is equal to a part of a matrix A. They're still not equal as matrices because they have different size. Let's define the first operation, the operation of matrix addition. First of all, you can only add matrices of the same size. And the way we add two matrices of the same size is we simply add the entries in the corresponding positions. This definition is very similar to the way we defined addition of column vectors. We simply add components which are located in the same positions. This is a binary operation on the set of matrices of fixed size because it takes two matrices as an input and it produces one new matrix as an output. Please pay attention to the fact that in the definition of matrix addition, the plus sign serves double duty. The plus sign on the left-hand side, which stands between two matrices, is the new operation that we are defining. This is the operation of addition of matrices. On the right-hand side, the plus sign stands between two entries of the matrices. And entries of the matrices are numbers. Therefore, the plus sign on the right-hand side means the operation of addition of numbers. Here is a simple example of matrix addition. We have two matrices of the size 2 by 3. Again, keep in mind, you can only add matrices of the same size. To add these two matrices, we simply add the entries which are located in identical positions in the two matrices. So in a sense, this operation is defined entry-wise. You can easily compute the result of this operation, so as you see, it is very easy to add matrices. The second operation, the operation of matrix scalar multiplication, is different from the operation of matrix addition in the sense that it combines two different objects. It combines a scalar, which is a number, with a matrix to produce a new single object, which is a new matrix. A scalar multiple of a matrix by a scalar is obtained by multiplying every entry in the matrix by this same scalar. And we do not use any special symbol to denote this operation. We simply use juxtaposition. We juxtapose two symbols, scalar and the matrix. Moreover, scalar always comes first, matrix always comes second. Here is an example of a matrix scalar multiplication. We have a matrix of size 3 by 2, and let's take a scalar, let's say equal to 7. So we are going to scale this matrix by 7. For this, we simply scale every entry in the matrix by this same number. And this is the result of a scalar multiple. As you see, it results in the same size matrix as the original matrix. When we defined the operations of addition and scalar multiplication for column vectors, we then observed that these two operations satisfy 10 specific properties. In fact, these operations we defined on matrices, the operations of matrix addition and matrix scalar multiplication, satisfy exactly the same 10 properties as the operations of vectors. Please take a very careful look at these 10 properties and compare them with the 10 properties which we discussed in this video. Please use the proofs of these properties for column vectors to construct similar proofs for the operations on matrices. I will illustrate how this can be done by proving one of the properties, let's say property number 8. As always, before you start proving something, I recommend to pause and ask yourself, what it is that I want to prove? In this case, we need to prove that two matrices are equal. What does it mean for two matrices to be equal? Well, we know that it means they have the same size and they have identical entries in the corresponding positions. The way we defined operations on matrices, they of course preserve the original size of the matrices, and therefore what we need to prove is that the matrix on the left-hand side has the same entries as the matrix on the right-hand side. And to prove that they have the same entries, we are going to take a generic entry in position ij of one matrix, and we are going to show that it is equal to the entry in position ij of the second matrix. First, we are going to use the definition of the operation of scalar multiplication to see that the entry in position ij of a scalar multiple of the matrix A plus B by scalar alpha is equal to the entry in position ij of the matrix A plus B multiplied by the scalar alpha. In the second step, we use the definition of matrix addition. The entry in position ij of the matrix A plus B is the entry of the matrix A in position ij plus the entry of the matrix B in position ij. But what we have now is operation on numbers, and we do know properties of operations on numbers. For example, multiplication distributes over addition. Now it remains for us to translate this back in terms of the entries of a certain matrix. First, we use the definition of scalar multiplication, and then we use the definition of matrix addition. Now, if you look at the beginning and the end of this computation, you will see that the entry in position ij of the matrix on the left-hand side is equal to the entry in position ij of the matrix on the right-hand side. And because I and j were arbitrary, this shows that these matrices have identical entries, and therefore they're equal as matrices. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. In the next video in this series, we will learn how to transpose matrices and how this new operation affects matrix addition and scalar multiplication. I will see you later.